So we have seen what is the meaning of conduction, induction. So we have seen the conduction, induction, and friction as a method to create charged bodies. We understood a bit about what is potential doing. So potential essentially talks about the overall repulsion of the system, and the electrostatic equilibrium, the concept of electrostatic equilibrium between two or more than two charged bodies refers to equality of potential. So if two or more than two charged bodies are at same potential, we say that they are at electrostatic equilibrium, and they won't be able to transfer charge if they are in already in equilibrium. So that is something which we studied. We also studied something called the quantization of charge, and what we realized that the creation of charged bodies is due to the transfer of electrons. So, and every electron can carry a certain fixed amount of charge. So whatever charge we develop must be the integral multiple of that finite charge, and that finite charge we call electronic charge. For electron it is negative, for proton it is positive, but numerically they are having same value. The plus minus, as we discussed, is just a convention. We should follow the same convention throughout. So the first question, the easy one. Let's start with the first question. How many electrons we must remove to develop 1 coulomb of charge on a body? That's very simple. I won't answer in 1 minute. So how many electrons we must remove to develop 1 coulomb of charge on a body? And body means it was initially neutral, and now we want to make it charged. And the charge that we would like to develop is 1 coulomb.
Hello.
Yes. Am I audible?
1 upon, hello.
Yeah, 1
upon 1 into 6
correct. So
into 10 raised to minus 9.
correct. So it's 1/1.6 10 power minus 19, which is equals to 6.25, I think, into 10 power 18. So this is a huge number, and to create 1 coulomb, we need to transfer these many electrons. This is really huge. The second quick question is, the transfer of electron will result into loss of mass or gain of mass. Is it true? Is this statement true that transfer of electron will result into change of mass? At least we can say.
Yes.
Yeah, that's correct. So transfer of electrons results into change of mass. Yes or no? So that's the answer is
Yes.
yes. So it's a very simple question which you answer. The third question is, what is the minimum charge possible on a body? What is the answer? What is the minimum possible charge that you can develop? Can we develop zero charge, like 0 point something something? What is the smallest value we can develop? I mean, it should be charge, of course. Zero cannot be the answer. So what is the non-zero value? The smallest non-zero value we can develop.
Sir, plus E.
Correct. Plus or minus, both is possible. You can add 1 or you can remove one. So the minimum charge you can produce is plus minus E. Okay. So now these are the just few questions that is based on what we discussed in the last class. And now we really need to start something called Coulomb's law. So let's begin Coulomb's law. So maybe from high school physics, you may be aware of the Coulomb's law. What is Coulomb's law? Anybody who knows, you can just comment.
That is F is equal to K Q1 up Q1 Q2 upon R square.
Okay. So Coulomb said that first of all, let me tell you very clearly, Coulomb's law gives the ability of one charge to exert force on the other charge. It is the ability of one charge to exert force on other charge. It is not the force itself. Like what you could have applied, what force Q1 can apply on Q2, assuming if they are kept in vacuum. So that is how we start the Coulomb law. We say that it is the ability of one charge to interact with other charge, assuming if they are kept in vacuum, and both the charge must be point-like charges. So this is the most basic assumption. If it is not the point-like charge, we cannot apply it. So let me put into words quickly. It is the ability of two point-like charges to interact with each other, assuming if they are kept in vacuum. Everything is hidden here in the definition itself. First of all, assuming if they are kept in vacuum is the word which you need to remember. They are point-like charges, and this defines the ability. I will just put a bar over this ability. So ability means like the ability will never change. And why this word ability I need to mention here? Because imagine if some medium will come in between the charges. Let's say you put the two charges in water, or maybe in some sort of between the paper, you insert some paper or some random dielectric. You put the two charges in the rajma chawal maybe, or maybe some shahi paneer. You put anywhere. You bring some sort of dielectric, they will not experience what Coulomb said. The experience is quite different concept, and the ability is a different concept. So two charges do not change their ability whether medium is there or not, but what they actually experience will change. So we'll talk about the role of medium and the concept of electrostatic force, which is quite similar to the Coulomb force with some modification. So what Coulomb said that the force of interaction between two point-like charges, assuming if kept in a vacuum, is proportional to product of charges and inversely proportional to the square of the separation. Pretty much straightforward. We know this fact, and therefore the product will be Q1 Q2 upon R square. And of course, in physics, what we do the moment you want to remove the proportional by equal sign, you need to introduce some constant. Let's call this k as of now. We'll put the value of k later on. And this k was computed experimentally, and the value of k turns out to be 9 into 10 to the power 9, roughly, not exactly, Newton meter square per Coulomb square. And the k we can also express in terms of some fundamental constant. What? So how we can express k in terms of fundamental constant? K is equals to 1 over 4 pi epsilon naught. Now this epsilon naught is something which we'll talk about in detail, but let's as of now, the epsilon naught is called, what do you call? Anybody? This is called permittivity of
Free space.
Okay, so the name is permittivity of free space. And do you remember the value? The value is how much? I think this value should be remembered by everyone. So what's the value of epsilon naught?
8.85 into
8.85.
minus 12.
Minus 12 Coulomb square upon Newton meters. Just reverse for the obvious reason. Now, before I proceed and describe what is epsilon naught in great detail, we'll talk about the dimension quickly. So, of course, dimensional analysis we can do everywhere. So, Coulomb is not the SI unit. As per the SI unit, we have the ampere, and charge is defined as current into time. So, we can say amperes second square. Newton is mass into acceleration. Acceleration is LT minus 2 meter per second square, and meter square is L square, and that as a whole will become the dimensional formula of epsilon naught. It turns out to be M minus 1 L minus 3 M minus 1 L minus 3. What else? T power 4 A square. So we got the dimension of epsilon naught, and that's why the epsilon naught is called dimensional constant. Dimensional constant. It is having dimension. There are constants which are having no dimension. They are just numbers like the refractive index of a medium. Absolute value is just a constant. There is no dimension associated. The Poisson ratio is just a number. The way you define the strain is again a constant. So there are many things which are dimensionless, and these constants are dimensional constants. So universal gravitational constant is dimensional constant, right? So now Coulomb said that point-like charges, because point is not the right word. What is point-like charges? Let's discuss one by one. What is point-like charges? So the point-like charges, do they need to be actually point, or it's just a concept? Okay. So if you have two charges and the charge is having random shape, so this will have its own dimension. Let's call the dimension as L1. The biggest dimension is L2. Now, if R is much bigger than either L1, not either, L1 and L2, if the linear separation between the charge is much bigger than their individual dimension, we call point-like charges. What we call point-like charges. Even if you put charge on the entire Mount Everest everywhere, not Mount, just entire Himalaya, and if you put the charge on some crater of other planet, maybe Pluto, then the interaction between them will be like point-like charges, because the separation is much bigger than what is their own dimension. So the rule of point-like charges is simple. It need not to be point. It just needs to be this particular relation. The separation must exceed or must be much bigger than the individual dimension. One thing I just forgot to mention, that not just point-like charges. We need to add one more thing here. I don't have space. Or charges with spherical symmetricity. What does it mean? If we have two charges or charge bodies which are definitely having some dimension, so let's say they have dimension of a radius r1 and r2, but the charge in that volume, is spherically symmetric. So it is spread out in a symmetric fashion. So whenever we have two bodies which are having spherical charge distribution, now the body should not be spherical. What we really emphasize is the charge distribution should be spherical. So for bodies with spherical charge distribution, and of course it is symmetrical, you can treat as a point charges, assuming the entire charge to be concentrated at its center. So where is the charge should be assumed, or
And
how the separation should be calculated? Only between the centers. So in case of spherical distribution, you must assume the entire charge to be located here and here. So if this charge is Q1 and this charge is Q2 as a whole, you are supposed to consider at center, and the separation between them will be the separation which you can plug into the Coulomb's definition. So only for these two cases you can consider the Coulomb's law. If these two conditions are not satisfied, the Coulomb's law cannot be applied. This is as simple as that. So I hope this part is clear. When to apply, when not to apply. Okay. So Coulomb's law we can apply for point-like charges or charges with spherical symmetry. That's it. So you can again put a note just as a reminder. Coulomb's law can be applied either for point-like charges or for charges with spherical symmetry. So if I take one sphere and if I put charge only on this side, another sphere if I put charge only on this side, can we apply the Coulomb's law here?
no,
No, because the charge is not symmetrical, so you cannot apply it. So Coulomb's law you should not apply. So just because the charge is given to a spherical body does not mean we can apply the Coulomb's law. The charge should be, the charge itself should be spherically distributed. What matter is the charge distribution, not the body shape. The body can have any distribution of charge, but unless it is not spherical, we cannot apply. So this is some do's and don'ts. There is some range constraint also for the application of Coulomb's law. So we say a range constraint. Range constraint for application of Coulomb's law. Anybody knows what is the range constraint? What is the range constraint? It is not applicable in the dimension of nucleus. So you cannot apply within the nucleus.
Sir,
So
what does range constraint mean?
means the two charges should be beyond the distance of size of nuclei. Like within the nucleus, you cannot apply. Let's say you cannot write for the two protons in the
Yeah.
nucleus. You cannot say that the two protons will follow the Coulomb's repulsion within the nucleus. Okay, or you cannot say that the two quarks will follow the Coulomb's law within their dimension. So within the nucleus, not dimension, I can say within the nucleus. It is not typical inside the nucleus. It's inside the. This is common. So you cannot
Yes.
apply for any particle which is living within the nucleus. You cannot apply the Coulomb. Only when the size of the nucleus becomes large enough, the periphery protons, the protons which lies on the periphery of such giant nuclei, let's say uranium or plutonium, those are mostly radioactive if you have heard about them. So they are radioactive because the instability is also caused by the birth of Coulombic repulsion. So in a small size nuclei, the Coulombic repulsion never come into existence. But as the size grows, the dimension outgrows the range of nuclear attraction, and then Coulomb's law comes into picture. So it also add to the instability of large size nucleus. So that is again you will study in the concept of stability of nuclei in a chapter of nucleus. So range constraint is also there, and one should be aware that you should not think of Coulomb's law for two protons inside the nucleus. Next. So now we'll talk about something more interesting that's called the electrostatic force. So what is electrostatic force? It is the force between two charged particles, not the ability. It is the force experienced, what they actually feel. Okay. So we say that it is the force experienced between two charged particles kept in any medium. Kept in any medium. So imagine if we have a medium and in this medium we have two charged particles Q1 and Q2. Now medium is also made of atoms and molecules, isn't it? Medium is also made of atoms and molecules,
Yes.
and every atom or the molecule will have electron and proton.
Yes.
So a medium itself is the collection of charge, although the charges are neutral because we have equal positive and equal negative charge. So what happens on the backhand side? The moment you bring two charged particles, or you can say charged bodies, in a medium. Now it's not a vacuum. It's a medium. Means you're surrounded by infinite molecules. Okay. Air is also medium in which the molecules are far apart, and it is experienced that the air does not affect the Coulomb's law by any significant value up to fourth place of decimal. Of course, the air can affect the answer in the maybe fifth place of decimal, and beyond that, up to 3 to 4 place of decimal, the air will not affect, and therefore we end up using the formula for air and vacuum in a similar fashion. We really do not make a clear distinction that air can have a slightly lesser force than vacuum, but that is something we ignore. In case of liquid or solid dielectric, let's say you have mica, paper, some sort of kerosene, you can say some liquids, dielectric liquids. In case of such dielectric, the interaction is in fact more significant. I mean, the interaction is something you can feel it. So the moment the charges are brought into a medium, the medium undergoes a process called induction. Now we have discussed about induction in the last lecture. So whenever a charge is brought into the medium, I mean, of course, the charge will start interacting with the opposite charge of that medium. I mean, it will attract the opposite charge of that medium and it will repel away the similar charge. So assuming that this is plus and this is also plus, it will try to bring some minus. Okay. And let's say this will also bring some minus here. Now this is invisible. I mean, of course, you don't see it. I mean, we have minus also, we have plus also, and we have so many other things. The two charges, because having similar polarity, they will repel as if they are in vacuum. So that will be the Coulomb's force. Coulomb force is the ability that they could have applied, assuming if there is complete vacuum. But this induction process will actually create a secondary force, which is normally invisible. You don't see it. So we say that when it is found that this medium exert their own force, and it is in the opposite sense. Always it is found in the opposite sense of the Coulomb force. So the medium, you can see that this negative charge is kind of pulling the Q2 charge. Okay. And this negative is kind of pulling the Q1 charge in the vicinity. They do this interaction, and therefore this invisible attraction leads to the decrease of the net force. So how much Q1 is actually experiencing now? So the force that the, okay, I can write Fe. Fe is called the electrostatic force. Now I have mentioned. So the actual force that the charged particle will experience will be the difference of Coulomb and the force that the medium will apply. Now it's very complex to write the force due to medium by doing the exact calculation. So there is a very simplified way of doing it, and we introduce a new concept, and that is called upsilon. Upsilon itself takes care of all the internal complexity. There is a derivation of upsilon. Of course, you can study in higher studies when you go for BTech. You can, and if you're interested in knowing the upsilon derivation, it is having very nice derivation based on the oscillation and so many things. So upsilon is now called permittivity of media, and the electrostatic force is now written as 1 upon 4 pi upsilon. It's not is not there. In the vacuum we use not, but in a medium we use upsilon. Q1 Q2 by R square. And this upsilon is actually taking care of what is happening here. So whatever is happening there, it will take care of itself. And you need not to subtract the two answers to get the answer. You can directly get the answer just by writing, or you can say replacing the upsilon naught of Coulomb's law by upsilon. And because upsilon is bigger than upsilon naught, you can clearly see that the experience will be less than Coulomb force. Do you realize this? What is happening? So epsilon being bigger than epsilon naught, the electrostatic force will be less than the Coulomb force. Coulomb force is still the same because that talks about the ability, and the actual force, the force which the charged particle will experience being in the medium, will reduce drastically, and epsilon takes care of everything. You need not to worry much about it. So now we have the third definition called the relative permittivity, and we write as epsilon r. Relative permittivity is also called dielectric constant. So a medium will have some dielectric constant. We call it epsilon r, or relative permittivity, and it is defined again to sort out the thing. So this is defined as the ratio of permittivity of medium upon the permittivity of free space. This ratio is called the relative permittivity. And because of this definition, if you want to reconfigure the formula in terms of epsilon naught, this term will needs to be multiplied. Epsilon r is of course due to medium only. For a vacuum, the value of epsilon r will be 1. For air, the value of epsilon r is roughly 1. There is a difference. Roughly 1 is after, I mean, maybe third or fourth place of decimal, the answer will be there. 1.00 something will be there. It's not exactly 1. And that is why the electrostatic force we can rewrite as 1 upon 4 pi epsilon naught epsilon r product of charge upon r square. And you can clearly see that the electrostatic force turns out to be the Coulomb force divided by the dielectric constant. And now I can make the use of this equation, the equation 1. Now you can actually find what medium applied. So the force due to the medium will be, so 1 implies force due to the medium will be F Coulomb minus F electrostatic, which is experience. And what we can write further? F medium is F Coulomb minus F electrostatic, which is equal to F Coulomb upon epsilon r, which is relative permittivity. And therefore, you can see the force due to medium is how much? Understood?
Yes.
So this is
Yes.
the relationship that you should be aware of. If the medium is conductor, the value of epsilon r is equals to, oh, not equals to, rather tends to infinity. So conductor is such a medium which will have the infinite permittivity, and therefore the F medium will be equals to F Coulomb, and therefore the electrostatic force will be how much?
0.
0. It means if you have two charges separated by conductor, it will prevent the interaction. That's the meaning. But it doesn't mean that they will not experience force. The force will be there, but due to the conductor itself. So now the conductor will apply the force, but the charge cannot apply force on each other. So bringing a conductor between two charges will stop the interaction, and the charge will only be interacting with the conductor itself. So we'll come to that in the chapter of Gauss law. In detail, we'll talk about the conductor and their various properties. So every other medium which is not conductor will have a finite value of epsilon r. I will particularly talk about water. It's very famous. So for water, the value of dielectric constant is roughly equals to 80, and of course it's a dimensionless constant. So why it is dimensionless? By the definition you can see here again.
Both
It's
same
very
quantities are divided.
dimension upon dimension, dimensionless. Okay. So it may be confusing, but it is dimensionless constant. It is value having 80 at room temperature. And I think it is having a value 81 at 0 degrees Celsius. Various textbook refers to the various number, but it doesn't matter much. And the epsilon r tells that water is able to reduce the Coulomb force almost by 80 times. So the moment you take a ionic salt, and ionic salt follows Coulomb's attraction or Coulomb's law, you can say. So when you put the ionic salt into water, what will happen? The moment you put the ionic salt into water, their Coulombic force will, the force will decrease by 80 times, and they are now weakly bonded. The force between them is very weak, and it is so weak that it separates. And this phenomenon we call dissolution. And that's why the water is called universal solvent only for the ionic salts. So why it is universal solvent? Because every ionic salt are bonded together by Coulombic attraction. And the moment you put into water, because of the high dielectric constant, the attraction becomes really weak, and therefore it dissociates into parts. That's a very easy way to separate the Na plus and Cl minus, and of course you can do further electrolysis to obtain Na plus sodium and chlorine as a gas. Because chlorine will become gas after reduction process. I mean, you can make this chlorine as neutral. It will lose electron. It's oxidation, right? So Cl will go oxidation. It is going to lose electron, and then it becomes Cl2 gas, which will vaporize or will leave the container, and Na will deposit. So you can get the solid sodium in the experiment. So this is what you might have done in the chemistry. Okay. So now you know that why water is called universal solvent. It's interesting to know about it. And now I will particularly talk about the permittivity again. So what is the meaning of permittivity? So whether you call permittivity of free space or medium, the word permittivity you can easily understand if you break into two pieces. The first is like called permission, and VT is like a VT is like something like resistivity. Now this will help you. So it's a permission and resistivity, which means when we have two charges or more than two charges, how they interact. So the mechanism of interaction lies in the concept of called electric field lines. Now, of course, we will discuss in a detail in a separate topic called electric field lines, but I will just give a brief introduction. So you can imagine that every charge is emanating some sort of invisible lines called electric field lines, and these lines needs to move through the medium or the space to reach the other charge, and that is how the interaction of the lines of the two charges, the interaction of the lines of the two charges, we call the interaction between the charge. So in reality, the charge don't interact. What interact is their lines, their electric field lines. So both charge creates electric field lines which move through the space and eventually they interact, and that in turn creates a force. Now we can say with simple logic that this interaction must be limited. Why? If the interaction is not limited, then force must be infinite. But even Coulomb said that if we have two charges at some separation, the force is having the limitation having some fixed value Q1 Q2 by K Q1 Q2 by R square. So if R is fixed, Q1 is fixed, Q2 is fixed, K is fixed anyway, the F is fixed. So a finite force says that okay, they interact up to certain limit. So vacuum offers the least resistance to interact. I'm not saying it's offering zero resistance. I'm saying least resistance, and therefore the permission is in a way the permission by the vacuum compared to the other medium is maximum. So the medium, the free space offers least resistance to permit the lines of force to interact with each other. This is how you can think about it. And therefore the permittivity is called the inverse degree of permission for the lines of force to interact. What we call? What is permittivity? You can put into words. It's a permittivity. It is the inverse degree of permission for the by the medium to allow the electric field lines to interact with each other. Okay. And that's very logical. I mean, the presence of epsilon naught you can see is in the denominator of the formula, right? You can see. No, wherever. So it comes here. So as this will increase, this will decrease.
Yes.
So we can say for sure that more the permittivity, lesser the interaction or lesser the force, isn't it?
Yeah.
So increase of permittivity will decrease the force. So can we say it's an inverse degree of permission by the medium to allow the electric field lines to interact with each other? And there is no medium which gives the zero resistivity. Okay, I mean you might not be aware of resistance of free space. I mean I'm saying actual resistance in the Ohm's law. And do not try to get this resistance with permittivity. The resistance of free space is actually 377 ohm, and the resistance of free space we write as Z, called the impedance, is written as mu naught by option something like this. Yeah. So this is the resistance of free space mu naught by option. Mu naught comes from the magnetism. That's called the permeability, the permission and ability. So when we'll talk about the magnetism, we'll talk about the mu naught. So permittivity is the inverse degree of permission, and more the value, lesser the interaction. That's logical. The water offers a very high value, and so the interaction the least. So Coulombic force will diminish by greater value, and so as we discussed, the ions will dissociate. Okay, so now this is not applicable for the organic swimming compound. Why? Because organic compounds do not follow the Coulombic attraction. They follow something like van der Waals attraction, or maybe something dipole-dipole interaction, or something more. So not all medium will have the similar formulation and similar law by which they interact, and therefore we cannot talk about the similar answer. Okay. So we will restrict ourselves to the Coulombic interaction, which is followed by the ionic compounds or ionic salts. Moreover, every medium will have some degree of resistance. Even the vacuum, you think that vacuum is not a medium, but even vacuum limits the interaction. Okay. So maybe in the dark space, the relation will be different. But what we write is not for the dark space, we write for the space, not for the dark space, because dark space is devoid of energy itself, or the dark energy behaves in a different fashion. So the Coulomb's law, how it will behave in the dark space is not experimented, because of the obvious reason we don't have dark space available where we can go and do the experiment. Okay, anyway, so we'll restrict ourselves to the world that we live in, and we believe that we are, I mean, the vacuum is everywhere. It's a space, it's not dark space. Mm. So the idea of a permittivity is clear, guys.
Yes.
Yes, sir.
So permittivity is the inverse degree of permission for electric field lines to interact with each other. And what we call force between the charges is actually the force due to interaction of electric field lines that the charge is capable of emanating. So they emanate, they create it, and by virtue of that, they interact. So that
Sir,
is
could
why
you
they
show
do not
previous
need
page?
a pardon.
Sir, could you show previous page for a few seconds?
Yes.
Yes, sir. Thank you, sir.
So now we can move towards. We can solve numerical, but before I think we can add one more topic, and then we can solve more numericals, and that is called the vector form of Coulomb's law, which is pretty interesting and easy and difficult for me. So vector form of Coulomb's law. So don't get scared. It's a simple writing the answer in vector form. That's it. So if we have gone through the vector chapter in past, this won't be difficult. If you haven't studied vector at all, this will be difficult. So before we discuss the vector form of Coulomb's law, I will just give a brief recap of something called unit vector. Okay. Short. So a vector, what is unit vector? A vector with unit magnitude and definite direction, right? So it must have a specified direction, but the magnitude should be 1. So we call it a unit vector. So given a vector A, how to find the unit vector of given vector? What is A cap? So to get the direction, to get the unit vector of a given vector, what we do?
A upon mod.
Very important. So dividing a vector by its own magnitude gives you the unit vector. So every vector A, if you know any vector and if you just want to convert into unit vector, just divide by its own magnitude. So let's say we have two like parallel vectors. What we have? Two like parallel vectors. You can say these are two like parallel vectors. Let's name it A and B. Are they having same length? No.
No.
Are they unit vector? Need not to be. We don't know. But they have same direction. Correct? So we know that they have same direction. So direction of A and B are same. So can we say direction of A upon mod A will be also same as direction of B upon mod B?
Yes.
So dividing by a
Yes.
positive number cannot change the direction. That's simple. If
Yes.
A and B having same direction, then dividing by the mod will not affect the direction. They are still having same direction. But now they have become unit vector, so they must be equal also. Understood?
Yes, sir.
So A
Yes.
upon mod A is equals to B upon mod B. Why? Because they are having same direction. So the rule is two parallel vectors, I mean two like parallel vectors will have same unit vector, or you can say will be equal. Their unit vectors will be equal. You can just simply say their unit vectors will be equal. Okay, so that's simple rule that you should know or should be aware of. And now we can come to the Coulomb's law. So we are trying to add the Coulomb's law in vector formulation, like not by writing the magnitude. So we had formula F equals to K Q1 Q2 divided by R square. Sorry. No. Just value. So the modulus is this much. This is the magnitude we have written already. Now we would like to write in vector form. So see how to express. So first of all, to write, let's say we have two charges Q1 and Q2, and this is some random origin. And what we know that the position vector of each particle from the given origin. So these two arrow represents the location of these two charged particles in free space. Let's call the first as R1 vector, call the second as R2 vector. All right. And now what we can do further is we can draw the X and Y coordinate. X and Y coordinate. Oh, really bad. All right. So we can rewrite, that's not an issue. X, Y, R1. So we have two charged particles Q1, Q2 having respective position vectors R1 and R2, as you can see. But to write the Coulomb's law, what do we need? We need separation. Correct?
Yes.
R1, R2 will never let you write the answer. You just need to know the separation, and that is why I will draw a line. Now I need to know this length. Then only I can write the Coulomb's law first of all, and also I need to know the separation, the magnitude part. So R1, R2 is there. So R1 is called the position vector of Q1 with respect to origin. R2 is the position vector of Q2 with respect to origin. Well defined. So the next part is what this arrow represents. If I draw some arrow like this, What is this arrow representing? Tell me
They're
about
attracting
no. Tell me about this arrow. Like this arrow represents what?
the direction of the
Yeah. So if I ask Q1, where is Q2? How the Q1 will point the finger? Okay, ask Q1, where is Q2? How the finger will be pointed towards Q2?
Ah, yes.
yeah
And similarly, if you ask Q2, where is Q1? The finger will be pointed like this.
Yes.
yes
So these arrow represents position vector of 2 with respect to 1. We bring the double subscript notation. If origin is not the coordinate system, if you choose some different reference point, we use double subscript notation to represent the same. Similarly, this arrow we can write as R1, 2. So what is R1, 2? What is R2, 1? These are position vectors of Q1 or Q2 with respect to the other. That's it. And what is R1, R2? The actual position vector. Is this part clear?
Yes.
Assuming both are like charges, let's say they have same charge, either both plus or both minus. Let's keep it plus as of now. If both are like charges, will they repel or attract?
Repel.
So what will be the direction of force on Q1, this way or this way? Up or down?
opposite side up
Up. So Q1 will be pushed upward and force on Q2 will be
Back.
yeah same backwards down
correct.
yeah
That's logical. So how to name it? This is the force on who is experiencing this force
1,
1
and who is applying,
2
2,
and this arrow represents force on
2 with respect by 1.
yeah. So 2 and who is applying 1. So the first thing you need to learn is the nomenclature, like how to represent it. Now tell me which two arrows are parallel. F12 is parallel with what? You can clearly see something. F12 is in parallel with R12
R1 2 yes
and F21 is parallel with
R2.
R2
R21. So these two vectors are parallel, isn't it?
Yes.
Like parallel. And again, we can apply the vector concept of unit vectors. Since F12 is like parallel with R12. Tell me guys, what should I write next? If two vectors are parallel, what must be equal?
Unit vector.
Their unit vectors must be equal.
Yes.
So F12 by F12 mod must be same as R12 by R12 mod.
yeah
And this term is also called E cap R1. If you know vector, this is pretty obvious. It's called the unit vector in the direction of R1. So if you want to connect like this, I will choose the first two relations, these two, to get my vector expression. So F12, because I cannot write the both force at the same time, I can choose one of them to write. I'm choosing force on 1 due to 2. That's good enough. You can choose F12 due to 1, doesn't matter. So what we can write F12 upon mod of, okay, this upon, and the mod of F12 is something which we can write with ease. It's a fairly the Coulomb's law which we have already written. Okay. So how to write the mod? Let's call the equation number something one. So mod of F12 is straightforward the F, the simple Coulomb's force. And how we write K Q1 Q2 by separation is square. What is the separation? Can we write separation as R12 whole square?
Yes.
And of course, you can write separation as R21 whole square. It doesn't matter. I mean,
Yes.
it's mod. And therefore, I will substitute back into the formula. So I'm done with the derivation. F12 turns out to be KQ1 Q2 upon the separation square into vector R upon the magnitude, which we can eventually rewrite as and this you can further expand as because what is actually known to us is the position vector with respect to ground, not ground, origin. Okay.
Yeah.
So because you know R1, R2, Q1, Q2, this is answer. This is the vector form. Very bad change. Let's change this. So to write F21, you can see there's a sequential follow-up, right? You can see there's a pattern 1 2 1 2 1 2 1 2.
Yes.
Follow the so 2 1 will be 2 1 2 1 2 1. So if Ij will be Ij Ij Ij. I hope this is clear.
Yes.
All right. So I think vector form is not difficult, but there is a caveat. There is something which you need to be careful. I'll put as a note. What is note? Okay, this is something which I need to explain. While using this vector formulation, and what I will say is, while deriving, I believe that they are having same polarity. What if I change the sign of one of them?
So then one of them won't be parallel to.
No. It will just reverse the direction. That's
Oh,
the repulsion will
Means
turn
they will
into
attract,
attraction.
right? Then
So they will no longer be repelling, rather they will be attracting
attract.
each. The arrow will switch. The F12 and F21 will switch. Like F12 will be this side, right, downward, and F21 will be upward, right? So how to take care of this sign issue? Because the derivation is only meant for the one part. So the direction switch can be taken care by switching the sign only. That's it. And the best way to do is substitute Qy and Qj with their sign while using the vector form. That's simple, and it's not very difficult. Just put Q1, Q2 with sign. If both are positive, they will be positive only. If both are negative, the answer will be positive. If one positive or negative, the automatically a minus will come into picture. which will take care of everything. So you're not supposed to worry about this. It looks a bit verbose, too much on the board, but let me show you an example and how easy is this to write. I mean, it's a really piece of cake. So how to write the force between two charged particles? So let me give you one example. So let's say we have a charged particle of value plus 2 microcoulomb, and of course, if you remember that to create 1 coulomb charge, we need to remove 10 to the power 18 electrons, which is just too much. So generally, the unit will be micro, nano, picocoulomb. These are very common commercial unit that you will come across. So let's say 2 microcoulomb is the first charge, and the other charge is, let's say, minus 6 microcoulomb in free space. Yeah, this is free space. If you want, I can show you some stars. You can see this is star. Twinkle, twinkle, twinkle. Okay, so now these are two charged particles in free space. The coordinate of the first particle is, let's say, 1, comma 0, minus 1. Oh, which plane? XZ plane.
X.
XZ plane. Yeah.
Nice. The other is 2, comma minus 1, comma 0. Which plane? XY plane.
XY.
XY.
Yeah. So it is like plus 2 is somewhere here, and like 1 minus 1. Somewhere here on this side. So X, Y. So plus X and 0, Y and minus 1. It's somewhere here. The plus 2 microcoulomb. Of course, these are not required at all. And minus 6 is where? 2 and minus 1. So 2 and minus 1 is upward somewhere here, or minus 1 is somewhere here. And the separation between them is this. And we are supposed to find the force between them without looking at the diagram. You can just do it mechanically and write like this. So you can just choose any one. Either you can find force on plus 2 coulomb or minus 6 coulomb. Which one you want to find?
Plus
Plus 2. Okay, let's say this is selected. Let's name it to 1 and this is 2. So you want to find the force on 1, and of course 2 will be applying. 1 cannot apply force on itself, isn't it?
yes.
So first of all, we'll add the formula K, Q1. So it's plus K, Q1, Q2 upon mod of R1 minus R2, which is pretty easy. 1 minus 2, how much? You can separate each component separately. 1
Minus
minus, so that minus 1 I cap. 0 minus minus 1.
plus J cap.
Plus G.
Minus K.
Minus 1 minus 0.
Minus K cap.
Whole cube. And what we need to write here? The same value, but without mod sign. There's the vector. No? That's done.
Yes.
Yeah.
How much time it takes? It takes just few seconds to write. Now, if you want to simplify, yeah, of course you can do if you have guts. Okay, let me do it. So the rule says put put whatever should be outside is the number. So sign must be in this bracket, not outside. So if minus is coming outside, put inside, and then you can attach 9 into 2 into 6. 9 to 6. Okay. Mod of ijk is root 3. 3 root 3. Correct.
Yeah.
10 power minus 6 minus 6 minus 12 plus 9 minus 3. And if minus was there, you can put it inside. So I minus j plus k. Because whatever is outside should be a number, just a number, plain number. I got the answer. So it's 3 to the 6, 9 for 36.
30.
I can add 12 with 3, no? 36 by 3.
Yes.
Into 10 to the power minus 3, I cap minus j cap minus k cap Newton. Done. And you can see that what is the force component in the x direction, what is fx value?
Yeah.
That's it. What is fy value?
Minus.
Minus, yeah. And fz is again plus. And given the mass of the charge particle, you can find the. Now, once you get the F12, there is no need to find the F21 separately because F21 will be Newton's third.
Minus of.
So whatever you got the answer, just change the sign in the bracket, the vector part. A minus I plus j minus k. That's it. So I hope this calculation is easy for everyone. Like,
Yeah.
not
Yes,
very
sir.
hard. So don't be scared of vector form. I'm not going to use anywhere. So for me, it is only useful to solve a few questions of Eroda that we'll see very soon. Otherwise, we can solve by common sense. We do not need so much writing to get one question solved. The J will ask the question, if they will ask question like this, in which they put the coordinates, we have no choice but to use the vector form. But if we can actually locate and see the direction, then we do by the common sense method. We'll see that also. Before I come back to the problem of vector form, I'll take you to the some very simple problems of Coulomb's law that everyone should be aware of. So the first question is, this is again point like, let me say, two charged particles are kept at a separation of 1 meter from each other. Just 1 meter, good enough. Okay. Find the minimum possible force between them. Okay. Okay. What is the answer? Just 1 minute I can give. So there are two charged particles at a separation of 1 meter. What is the minimum force possible? I mean, it's a puzzle. It's not a physics. It's just a puzzle. Can you solve this puzzle?
We can directly put it in the formula.
Yeah, tell me the answer.
9 into 10 raised to 9.
Very good.
Yes, sir. Same.
Yeah. So the answer is K square. The minimum charge possible on a charge body is E. So we cannot have charge less than this. And with minimum charge, we can have the minimum force. The answer is K square. Excellent. Next question. So next question is, if we have two charged bodies, So two charge particles are kept at a separation of d. If the total charge on system is capital Q, find the maximum force between them. Maximum force, find the maximum possible force. So what you don't know that what is charge on first particle, what is charge on second particle, what you know is the total charge is Q. So what is the maximum force possible? I can give 1 minute to solve this question.
Hello.
Yes.
A Q square by 4D square.
Yeah, that's the right answer. So maximum force will be when the charges are equal, right?
Yes.
Yes, sir.
Why charges are equal? So let's say we don't believe they are equal, so we can add K. The first charge is X, the other must be. And this is a simple function of X. When the function is maximum, then X is Q by.
Yes.
So for F max, you can differentiate if you want to 0, and this will give you X equals to Q by 2. And that's very pretty much a known answer in the maxima, minima. We have solved in the mathematics also in the very beginning. So the
Yeah.
d by dx is, I mean, of course, this is x is. So when the charges are equally distributed, the force will be maximum. That's it. So let's do the next problem. So if we have two charged bodies identical in shape, size, and they have same charge density rho and rho each, and they have same radius r and r, then the force between them will be a inversely proportional to r square, inversely proportional to r, directly proportional to r power 4, directly proportional to r square. So which of the following is correct? And maybe I have made wrong mistake, so I can put it last. None of these. Safer side for myself. Let me play safe. So this is none of these. If something goes wrong, E will be the answer. Tell me the answer. Time is 2 minutes to solve.
Hello.
Yes.
So I think it will be none of this.
So what is your
Because
answer? What you're getting?
it will be inversely proportional to 1 by 4r square, right? Because the
So this is the answer.
ha,
What is proportional to R now? 4 is the number.
yes, A will be the answer.
So one choice I got the answer is A. Let's see. Anybody else?
Sir, even I say A.
So two guys are going for A. Anybody else? Okay, the right answer is
Yes. And
C.
See,
Yes. So the force will be density. Okay, how we write? K Q1 Q2, so it's K Q square
yes,
upon R square. It's like 2R square, so 4, you can say 4R square. So, but the charge is not given. Charge is not given. What is given? Density. So rho into 4 by 3 pi R cube is the charge. Density into volume. So rho is called the charge density. Just like you studied in the center of mass chapter, the lambda, sigma, rho. So R power 6 upon R square. What will be the answer?
4.
So as the sphere will grow, not just R will grow, the charge will also grow, right?
Yes, no.
Therefore, the relationship will be fourth power of R. So C is the right answer. Okay. These are some simple puzzle problems, like easy one. Now, if I give you a rod of certain length and certain charge, let's say a rod is having a total charge Q, total length L, and it is uniformly spread over the length. And from the center of rod at a distance R, we have another point like charge Q. So can we apply the Coulomb's law here? Can we apply the Coulomb's law directly here? Am I audible, guys?
I don't. No, I think because charges will need symmetry, right?
So of course, the rod is not point like charge, right?
Yes.
And it is also not mentioned that R is much bigger than L. R is given, so we cannot use
Yes.
the concept of point like charge. Okay. So then what we can do? Then how to find force?
sir, integrate.
Yeah. So what you can do is you can take elementary part of the rod, and every elementary will become a point like charge, which you can apply the formula. So the way of solving is pretty much simple. So the Coulomb's law, we cannot write for the rod and the point charge, but you can write for the particles. So if I write df equals to k dq1 dq2, I mean elementary upon separation of the elementary. So one is itself particle, so we need not to worry about it. And the other I have to take. So how we take elementary, and I hope by this time you are mature enough to
Cut
understand
deal.
elementary. So how to take the variable and how to cut it. So the small q itself is particle, so we need to know the distance of various elements from this charge, right? So I'll move some random distance called x, and while coming here, I'll cut.
Cut dx.
So dx is not the distance, dx is the particle dimension that I have cut here. So this this charge in this length. So x is the distance at which we have taken a charge. We can call this charge as dq. And this charge dq is spread over the length dx. Okay. So now this charge dq is having a definite separation from the q. So force between them will be how much? K q1. Oh, let's confusing. Let's make it dq dash because I cannot choose the same symbol. So k dq dash into q2 upon what should I write here? Apply Coulomb's law now. K q and q2 by r square. What I can write here?
X plus
X plus X plus.
That's always you make mistake. X is the distance. Dx is the dimension of object itself.
Okay, X square.
Only x square. Dx is not the dimension. X is the distance at which this elementary charge resides. It's the Coulomb. We have discussed this many times. So you move x away from the q, and then you get a point charge dq dash, which lives there. And of course, dq dash will have its own dimension. Pretty small compared to x, we can think as a point. So what is the distance of dx from or dq dash from q charge? The distance between the q and the dq dash is how much?
Sir, R plus X. No, R minus X.
What is the distance of dq dash and the small q? Don't try to apply brain. Just look at the diagram. You will get the answer.
X.
How much? It's a visual thing. You have to see the diagram and tell me the answer. What is the separation between dq dash and the charge q kept there?
X.
X.
So where is the rocket science in this? I mean, you're saying something random. So how to convert dq dash into x variable? So what is dq dash by the way? It's the charge over the length dx. So we can use the definition of lambda as I have discussed the center mass. So linear charge density we can call lambda.
Yeah.
So what is the density? Charge per unit length. So in the length dx, how much charge is there? Dx. And by default, because charge capital Q is spread over length L, so lambda is well known to us. Q by L. Understood?
Yes.
Yeah.
Simple unitary method which you always fail to apply. I don't know for what reason, but maybe in class 4th or 5th, it was the most challenging part, unitary method. So dq dash turns out to be how much? That's common. I don't know why I am teaching this part. So if L length having charge q, so one will be having q by L. So dx will be having q by
Q
L.
by L dx.
I hope this reminds you of your kindergarten days.
Sir, I can give answer.
So now, can you answer the question? How much is the answer?
Sir, final answer, K capital Q small q R plus X.
Yeah, go ahead and tell me the answer. So net force will be integration of this, and we keep the only variable inside
dx by
Minus
X square.
KQ.
minus kq.
No, minus no.
Okay, what will be the limit of integration? Tell me the limit first.
Sir,
And why we need to take limit?
0 to R.
Oh,
Extra.
0 to r,
R to R plus X.
r to r plus x. Very good. Okay, you do not understand anything about mathematics. Why we take limit and what we are doing here. The limit is taken to cover the rod actually, because the rod will have infinite such elementary dq dash. So how x must vary to cover the rod? Tell me. As x will vary, it should take care of every part of rod from the beginning to the end. How am I going to achieve this?
So whole rod. So
Common sense. These are common sense. Nothing about physics. You have to cover the rod. X is a variable which will vary in order to take care of every element. So how x limit must be decided? Tell me.
to cover the rod.
Yeah. Okay, tell me, if x is 0, are you nearby the rod?
Yeah.
0 means what? Where you are at Q, na?
Oh yeah.
So rod doesn't begin at Q. Where the rod begins?
At X.
At x. Great. Rod begins at x. X is a variable with us.
Oh yeah.
X is a variable which we must vary to cover the rod. So how we must vary it to take care of the entire rod? No. And none of you are getting the idea. I mean, what is X doing here? I mean, don't do it blindly. Try to see the diagram. I think try to increase the visual inspection. Look at the diagram carefully. You will get the answer. It's written there. Imagine the rod is the mall. Q is the your home. How much you must move to reach the mall first?
L.
L. So if you walk L distance from the small Q, you will reach the mall. Huh? Let's say the right end of the road is the entrance and the left end is the exit. So to reach the entrance, how much you walk? No common sense. Common sense is missing entirely in the earth. I should leave the earth. I'm going with Elon Musk. I will be on Mars. Not interested here. This is the beginning of the mall. How much is this length? Tell me. Common sense. Very difficult thing in this universe. I hope now you can give the answer. How much you must move to reach the entrance?
R plus L by 2.
Is the entrance or exit?
Like total, I'm telling the upper blue line color.
No. Where the road begins?
R minus L by
Exactly. R minus L. And where the road ends?
R plus L by.
Exactly. Imagine just looking at the diagram and writing the limit is so difficult. So you haven't really worked with elementary in the CM chapter. So elementary is a concept. You need to understand it's not something randomly you do and you get the answer. It's not something you just integrate out of blue and you get the answer. You do something logical. And what you do is you try to incorporate the formula for a given situation. So we know that Coulomb's law is only applicable for point-like charges. Now given situation is not following it. So in order to follow the Coulomb's law, I need to take some elementary, that is a small piece of rod. because that small piece of rod will act as a point charge. The other charge is luckily the point charge, so we can integrate, isn't it? Understood?
Yeah. Yes.
So what you are doing here, you are making it possible. What you are making it possible? The Coulomb's formula. And to make it possible, we need to do something logical. What we need to do? The one charge is point charge, so we need not to disturb it. It's as good as we want. The rod is the issue. So you cut a small piece of rod and you choose the distance from the actual charge as x. You can choose x from somewhere else also. You can take the right end of the rod as the beginning, and then you can also move x from there. Not an issue. But the way you write, you have to change the limit. Let's say if I choose the limit in this fashion, think about it. Just for discussion. If someone is choosing the x from here, I call it a z and I cut this as dz. So what will be the limit of z to cover the rod? Tell me the answer. So to cover the entire rod, z must vary from where to where? Am I audible, guys?
Yes.
Hello, 1 2 3 1 2 3.
Hello.
Am I audible now?
Yes.
So tell me, what should be the limit of z to cover the rod? Oh my God. Is my question clear? No. Am I audible, guys?
Yes.
Tell me the answer. For what value of z the rod will be covered? Anyone who can answer? So now z is the new variable. So what should the limit of z so that the rod is covered? Like every element of the rod is taken into consideration.
X minus Z, and
The z begins from the rod only. The right end of the rod is the beginning of z.
yeah, so for the beginning of the rod, like it would be like the distance. Oh, yeah, so that distance is, oh, never mind, yeah.
So how the z should vary from where to where to cover the rod? Of course, 0 to L.
0 to
Right?
L, right?
It's right. So 0 to L is the variation. But now how I should write the Coulomb's law in terms of z? So here, if I want to write the answer in terms of z, the df will be how much? K. Tell me, what should I write here? In terms of z. How the df should be written now? Tell me.
K Q by L
Hmm.
or Q D Z.
Okay. or you're trying to just
No,
manipulate the answer? Yeah.
that
Okay. Okay. Upon
z square.
Huh?
Uh,
Is that the distance between the Q and the elementary? So what is the separation between the elementary and the point charge Q? Is it Z? Are you sure?
x only.
But X is not now. Now we need to express in terms of Z only. We
X
have
minus
changed the
Z.
variable.
X is not.
No, we cannot use X. No? Our elementary has changed. Now I want to express in terms of Z actually. What should I write? Think about it. This thinking will open the door for further visualization. You will
R
be
is
able,
there, right? Like
R is there, L is there, of course. You can use R, you can use L, you can use Z. Nothing more, nothing less. Until you're not answering this question, I'm not moving forward. You are also stuck, I'm also stuck here. Yes.
R minus L by 2
Mhm.
plus Z.
Exactly. Excellent. R minus L by 2 plus Z over this is the answer. And when you integrate here, the limit will be 0 to L. That's it. You need to realize what exactly you mean by limit or what exactly you mean by the elementary and why you are doing this. Until you are not realizing these three parts, do not proceed. Don't try to mug up the process. You have to integrate is not the answer. Understood? We are not doing something out of compulsion. We are doing something, we are taking the step which are logical. I mean, they have their own logical flow. I mean, I'm not doing it from my side. I know that this is the only way I can do it. Until you do not realize the meaning of elementary, you haven't learned about element. Then 40-50% of the JE advanced preparation is based on integration, elementary. You have to feel comfortable with this. Let's take one more case of elementary, and I hope this will give you enough practice. I have some space left. So what if I choose elementary from center? So let's say I move Y and I cut a D off. Or maybe I should have taken on the right side, but that's not. So in terms of Y, okay, first of all, how to cover the entire Y? So in entire rod, I'm taking Y positive on the left side, the right will be then negative. So what will the limit of integration in terms of Y?
0 to L by 2.
But that will cover only half length. I want to cover the entire rod.
Acha.
Think about it. I always say, always do the derivation till you realize it. Correct. So the limit of integration will be minus L by 2 to plus L by. Of course, these are coordinates and you have to take care of the sign also. If you move in only one direction, take it positive. If you move in two directions, take one as positive, other as negative. So your limit of integration is from minus L by 2 to plus L by 2. Simple enough. But how will I write the Coulomb's law then? dF equals to how much? Tell me.
K Q by L dy by R plus Y the whole square.
See, now you have three choices to integrate. Now, this question can be solved in three ways. Now, it's totally up to you to choose the way of writing. Some way will be easier for you, some way will be difficult for you. And that is how the integration is done. We are actually very much free to choose. And the right selection will make this really easy. So you all can now solve and tell me the final answer. Choose whatever method you want and tell me the final answer. So which one is the easiest, I think, in terms of which one? X, Y, Z.
Sir,
Like
X is easy.
it's up to you. You can choose whatever. All
X
are
is easy.
yeah. I think the Y is also easy. Z is also easy. I don't know why you're saying difficult. Anyway, so tell me the answer, final answer. After so much hard work, now you can give me the answer.
Sir, I'm getting it in minus.
So it must be wrong. So what is the integration of 1 by x square?
Minus 1 by X.
Are you putting the limits, upper limit, lower limit?
Ah, yes. 1 minute, I will check again. Ah, now I'm getting it positive. Yes.
Okay. So what is the answer?
KQQ by L. No, L will get cancelled. KQQ.
That's right.
Yeah.
So the final answer is KQQ.
4.
Four.
4KQQ.
For numerator,
No.
you say?
4KQQ. Numerator. Ah, yes.
I think this is the answer.
No, wait. It's 4KQQ upon 2R square minus L square after simplifying further.
So this is the answer, no? This is the answer.
Yes. Yes. Yes, I just okay.
You are saying this way, right?
Yes.
So pretty simple question. You have taken almost half an hour. You could have done this faster. Anyway, so I hope this will clear your thought process about elementary. Of course, we'll do the continuous charge distribution calculation later on. Right now, we are doing a simple question. So now this is again a very typical question. Two identical conductors. Just so now the question is three identical conducting sphere. So you have three conducting sphere. One, two, three. Let's name it A, B, C. Now the sphere B, okay, now let me tell you the separation. This separation is given as D between the centers, of course. The sphere in the middle is given a charge Q. Now Q will go on touching A, so Q will first touch A, and then it will touch B, touch C. So you give charge to B, B will touch A, and then B will touch C. In the process, some charge will transfer to A and C, and then B is removed. So the entire question is B is given some charge initially, then B touches A, and then C, and finally it is removed. Okay. Questions clear? Hello, hello, 1, 2, 3, 1, 2, 3.
Hello.
Yes. Questions clear, guys?
Yes.
Solve it. Tell me the answer. 1 minute is sufficient. So when you touch A will get how much charge,
Q by 2.
and C will get how much charge?
Q by 2. Q
Because
by,
only Q by 2 is left on B,
oh yeah, Q by 4.
and then it will divide again half, and now the force will be this much. So it's 8. Yeah.
Yeah, it's a got.
So next question is called. So of course you will deal with this question very often in this chapter. So let's begin it. So imagine you have a question like this. So you have a spherical charge, and the total charge is Q. So from a spherical charge, a part is scooped out. So what you do is you remove a sphere from the sphere cell. This is exactly R of the big sphere, and there is a point charge. And the distance of this point charge from this sphere is, let's call it 3R, and we have the point charge, let's call it again Q. You can call it anything. So question is actually from a sphere of charge capital Q, a small spherical cavity is made of radius R by 2 as shown in figure. Find the a point charge of same magnitude is kept at a distance of 3R from center of a sphere. Find the force between them. So this is a pretty straightforward question. The question is what? You are supposed to find the force between this big sphere and this small point charge. Numerically they are same, but the one is point charge, other is the charge which is totally spread. Now, what this principle of superposition says that this is, if you remove a part of a sphere, it will lose the symmetricity, and because it will lose the symmetricity, you cannot calculate the or cannot apply the Coulomb law because it is no longer a spherical charge distribution. The moment you remove it, it simply removes the symmetricity. Then how we solve it? So what we do exactly? So we assume that the full sphere is present. We find the force. We assume the small sphere is present. We find the force, and then we subtract. Why we subtract? Because it is actually not present. By doing this calculation, we maintain the simplicity individually, and we apply the Coulomb's law. Once again, You can imagine this part is filled rather than empty. Now, the moment you fill it, you complete the sphere and you can apply the Coulomb. You also apply the Coulomb law only for this portion, the portion that you are removing, assuming it is present, and then subtract their answers. Why? Because the big sphere will create the field like, will create the force like this repulsion. So the F1 is, let's say, force due to the entire thing, but this entire thing will be equal to the force due to the which color is this? Can you tell me which color is this? What?
Blue.
No, this color. This one.
Oh, that is light shade of blue only.
It's blue.
Light shade. Very
I think it's green. I can see as a green. I don't know.
maybe.
Okay, so let's say the net force, I can tell you. So the total force F due to full sphere will have the support of F due to the pink sphere, F due to the green. Can I write like this? Because they have same direction. So the full sphere will be having the force due to the pink part and the green part, assuming pink is also present. Nothing is removed. Okay. So F due to the green part is how much? So this is how you can solve by manipulation. Understood? So I'm removing this. Let me show you on the other page. So any question of superposition?
Like we did in the truncated bodies.
Yes,
Like
that's
that.
similar idea. So what you're supposed to do is take the full object, find the force, take the small object, find the force, and then remove the answer because it is actually not present. This distance is 3. Can you tell me what is this distance? The center of the cavity and the charge, given charge?
3r minus r by 2.
Yeah, 3r minus
R by 2.
r by 2. What is that?
5r by 2.
IR
Very good. So you got the D, and now you know the okay how to find the Q charge. You can use the unitary method again. The volume proportionality. The charge will be proportional to volume. So Q is proportional to RQ. Sorry, R by 2Q. And capital Q is proportional to what volume? RQ. So you can say Q by Q will be 1 by 8. So you can directly get the answer Q by 8. Like whatever you want to do, you can do. I just did like this because charge will be proportional to volume, and volume is proportional to R cube. So I just use this relation to get the answer directly. It's up to you to solve the way you want. So I will not teach you the unitary method right now. Okay, that's very long time we have done this in class 6. Okay, so now what we'll do next is we'll find the force here. Let's call it F1. F1 is how much? A q square by 9r square because it's a spherical
Yeah.
body. It is simple. And F2 will be how much? KQ q by 5r by 2 whole square. Correct? So this will become 25 by 4 r square. And what is q? Q by 8. 4 to z. This we can see, no? 4 to z. So KQ square by, it turns out to how much? 50 r square, right? Tell me if I'm wrong in calculation. Generally, I am. So, so the
You are
net
correct.
force,
Yes,
the,
sir.
the actual force will be how much?
F
F1
for
by,
F2, F1 minus F2, sorry.
so KQ square by R square, and I'll write 1 by 9 minus.
41 by 4.
Yeah, whatever it is, I mean, I don't care. So this is how you apply the principle of superposition. Something, if you remove from a portion from a symmetric body, which itself is symmetrical, you can fill the gap, think as a full body, find the answer. The gap part you can think as separate body, find their answer, and then try to subtract. But while subtracting, you have to be very careful. These are vector quantities. You must subtract in a vector form. You cannot just subtract like in numericals. Here I simply subtracted because the direction was same. Is this clear?
Yes,
Yes.
sir.
So how we can make it a complex question like this? So from a big sphere, we remove two cavity, one here and other.
So for this, we will subtract 2 times, right?
No, if you subtract two times, you'll get the wrong answer. Why?
Oh,
Because you are not taking care of it's a vector quantity. Force is a vector. So the cavity will pull the charge in this direction. You can think like the cavity as a negative charge, like opposite charge. Think this way. That will be easy in terms of solving. So the full sphere will pull this way. Let's say, sorry, the full sphere will push this way. Correct?
yes.
So then, like instead of adding, you can think like this part will. I mean, this part will attract. I mean, just we can change the nature of charge cavity. So you can think as full charge. So this is how we think. Full charge is, let's say, Q, and this charge, this part is removed. So we can think this part is filled with same charge and remove the same charge. Like whatever the charge Q plus Q minus Q plus Q minus Q. How to say it? I hope you all understand this part.
Yes.
So the simple ways, the full sphere will repel and these two will attract. And you can think that everywhere charge is present accordingly. You can say F2 and this is also F2. Theta, this is also theta. So the net force will be how much? F1 minus 2F cos theta. Now if you just simply subtract two times, you'll get the wrong answer, isn't it?
Yes.
Because we are doing the superposition of force, and force is a vector quantity, and vector quantity must deal with the direction. So the previous question was actually luckily unidirectional, and therefore we never felt the need to think about the vector notation. Understood? So now we are doing the same question. So the total charge, now I'll just change the question. If the remaining charge, if the remaining charge is Q, then find force. This is again challenging. So what I'll do is I'm giving this as a homework. You can think about it carefully, spend some time and solve it. Okay. So what is given is not the full charge given. What is given? Only the remaining charge, the charge which you see actually. Earlier we had a charge Q and we removed it. Now we are not removing it. We are like removing from charge Q. We are after removing the charge left is Q. So initially it must be more than this, isn't it?
Yeah.
So you can think about what was initially the total.
And the length, like the radius is R, right?
Yeah. So radius will have the same relation which give you. This is R by 2, and the bigger one is R. Okay.
The distance is
3R, same.
okay. Sorry.
And the distance we will keep as again 3R. So solve at home, and next class you have to show me. Now we are going to deal with some conceptual question of Coulomb's law. Then we come to the the vector form again. So some conceptual question like okay, let me just name it two conductors. I don't want to name it complex name. Imagine you have two conductors, quickly 1 and 2, and they have their own radius. Let's call it R and R. And their separation, let's call it D. So what we do is we give some charge. Let's say we give charge Q here, we give charge Q here. And D is not very bigger than R. So D is quite close. D is of the order of, let's say D is maybe 2.5 R. So D is quite close. You can consider 2.5 R means the gap between the sphere is really small, right? So
Yes.
ideally what happens if you give charge to any conductor, let me tell you some property. The conductor will spread the charge over the surface only. The most important characteristic of conductor is no charge given to conductor can go inside. It remains on the surface itself. So there is a rule, or you can say just the theorem. And we note any extraneous charge given to conductor only remains on its surface. Yeah. So any extraneous charge, it means it will have, of course, positive and negative charge inside the volume that we cannot disturb. So if you give something, it will be go on the surface. And the second thing is, in case of conductor, charge can actually move over the surface. So they are free to move over the surface. The second point we can add is charge on the surface of conductor are free to move. All right. So charge on surface conductor are free to move. I mean, if they want, they can move. So why I'm discussing all this? Because you're giving charge to conductor, but they are very close, so the repulsion will let them move actually. And if they are like same polarity, the repulsion will make them move. So as a result of this repulsion, what will happen? You will end up getting more charge on the back side and less on the front. Do you realize this?
Yes.
And similarly, less here and more on the back side. That's the first question first. Can we apply the Coulomb's law?
So because the T is small,
We cannot apply because it's not symmetrical. The spherical charge distribution is not there. We can only apply for spherical distribution or point charge. Here nothing is happening. Neither it's a point like charge nor it is spherically symmetric. Okay. So the answer is no. We cannot apply. But we can compare. So let's say if charge were uniformly distributed, if charge were uniformly distributed, then the force between them would have been written as k q square by d square,
D
right?
square. Yeah. Yes, sir.
But this is like a kind of expectation. If something would have been like this, then we could have written like this. Unfortunately, this is not the case. So now the force is acting, which is not this force. Can you tell me only one thing? Is the actual force more than this or less than this? Like whatever is acting is going to be bigger than this or less than this?
Sir, bigger than this KQ square by D square.
So the new force, the actual force is going to be more than this. Why? Why you said bigger?
Sir, because
Because
um, two, no. So just a second.
anybody else who want to give some logic, like if the new force, like the actual force, is going to be greater or lesser than the case when it would have been symmetrical.
I think less
Yes.
because the charges are less on the outer periphery.
Okay. Anybody else want to say something?
Sir, our charges on the surface are free to move.
Okay. They have moved already. They're not moving now further. Like they have gone like this and now they have stopped.
They will be greater because it is not distributed uniformly.
It is better because,
Not distributed uniformly.
but non-uniform will make it greater. What is the logic? Why not lesser than?
Yeah.
Sir, because bulk of the charges get farther away from each other, so
Exactly.
distance will be
That-
more.
Yes, exactly.
So the right answer is the charge center. Even there is a concept of center of charge. You know, center of mass.
Yes.
Now in nature, as I said in the very beginning, the entire universe having only two properties, two fundamental characteristics: mass and
Mass
charge.
and charge, yes.
Both follow the similar concept, similar, you can say similar ideology. So just like center of mass, we do have center of charge. And what we can say that the effective center of charge is shifting right and left for the right sphere and the left sphere. So what we need to realize that the center of charge for this sphere has somewhere shifted here, right? We can call COC because the more density is right, so this becomes a center of charge, just like the analog of center of mass. And similarly, this is the COC for this sphere.
Yes.
So we can say the effective separation has increased, right? That's clear.
Yes.
The effective separation has increased, gone up, and the force must decrease, right?
Yeah.
Now, of course, don't try to apply the Coulomb's law, but this is the sufficient hint to realize that. So we cannot find the actual answer, but we can say that the actual force will be less than the Coulomb force that we can expect. So that is the problem. Like the moment you bring conductors closer, they fail to follow the Coulomb's law because the charge can move freely, so they will move to minimize the repulsion. And as the action, the center of charge will shift, and therefore the net force will be less than the Coulombic force, assuming if the charge is symmetric. Now, similarly, what will be your answer if I reverse the polarity? So same situation, but with reverse polarity. So let's say you make one plus q, another minus q. Now, if you make one plus q, another negative, what will happen? The attraction will bring the charge closer more, right?
Yes.
Yeah.
So more plus here and
So
less
force
plus here.
will be more now,
Yeah,
as D will be less.
correct. So the effective distance will decrease, and more negative will be here, and less. And now what we can say that the center of charge will be closer, so that the D effective will be. So F actual will be more than F. So these are some of the conceptual questions that you should be aware of. Now you can begin solving a theorem. Of course, we have only discussed the scratch. It's just a sketch of the surface. We haven't discussed much of the problem. Now, the other variety of problem which is based on the vector form of Coulomb's law, we'll start in the next lecture. And I will request all of you to start solving right away.
Yes.
So start solving from the basic. Most of the error problems I will discuss in lecture only. No need to solve at home as of now. Once you are finished with the experiment and once we are done with the chapter, you can go and solve the remaining question of error. So because 80% will be solved in the classroom, and you will get some 20 to 30% to solve at home, which you can practice. Okay.
So
Sir, I wanted to ask one thing.
Yeah.
Sir, this year mains is now happening. So from where we can get the papers of that of 2022?
Papers I can send right away. I have right now.
Yes.
Just a moment.
Okay.
Sir, so we should start with Herodov. Huh?
You solve for SCORM, like start
Okay, yeah. Sure.
SCORM. Error problem you should solve with me at in the lecture only. Like normally I give error problem in the class.
Yeah. Sir.
You first get the hang of it. Don't try to attempt at home and spend your time, or in fact I would say waste your time. You attempt here, try to realize. Once you have confidence, once you have done the basic problem of SRO, then start solving. Okay, so
Even we can solve the sheet, right?
that is the best. I mean, sheet is the
Yes.
best, but if you take something which you can finish at least. If you take the sheet, then make sure that you are going to finish it.
Yes.
So have I shared the sheet of electrostatics?
Yes, you have.
Yeah.
Anyone who has not received?
Sir, I,
Yeah, you have. I mean, okay, you have come late. So okay, I'll share just in case.
Sir, I have also not received.
I'll just a moment. I'll send right away only. Okay, this is the question paper I have shared. Let me share the electrostatic sheet also. Now I will tell you few things before you start. See, the time constant is there for everyone. What I want is that whatever you begin with, let's say someone is doing SC or someone is doing the sheet or someone is doing Erodub, make sure that you finish what you start. Don't solve one, two questions from here and there, then three, four from here and there and learn that way. No. You start from SC or make sure that you do end to end. The last question should not be left. Also, from class 12th, what is very important is the objective 2 of SC for everyone. So make sure that you all practice objective 2 of SEO, everyone. Objective 1 and objective 2 both. So this is very, very crucial for competition. Objective 1 and 2, and then you start the exercise. But right now, you have to do the 1 and 2 at the end of the chapter because these are mixed problem. Don't try it right now. What you need to start right now is exercise problem. So at the end of your chapter, you must make sure that you can solve all these questions. Okay. And Erodub, I will start and then you can also start. So just wait for some time. Erodub, we are going to discuss in detail. It's easy only, but only when I will discuss. So your homework is start from sheet. Now sheet is really nice. Why it is nice? Because every part is separated. You can see clearly that they mention properties of charge and Coulomb's law. So you can just solve. So now what you can solve? A1 from where? Exercise 1, A1. Now, if you are solving sheet, then don't solve SEO. Why? Because most question of SEO Verma which are good is somewhere present in the sheet. Okay. So your homework is exercise 1, A1, page 5 of PDF. Then okay, I think that's it. If you can solve on your own. But I have taught up to this level. After next lecture, you will have too many homework. So one more lecture, and then you will have sufficient homework to solve. So gradually we are moving towards the topics. Okay, so whatever you choose, whether you choose SC Verma or you choose sheet, make sure that you finish end to end. Unless you're not solving end to end, there is no benefit. Don't try to solve by scattered way, like doing few terms from here, then from there, and from some other sheet and so on. No, just stick to one sheet. That's sufficient.
So,
So all right,
and for
guys.
rotation, I will complete it by this week so we can have doubt solving the next week. Is it
Yeah,
okay?
definitely.
Okay.
So anybody else who is doing rotation? Anybody else? I think
yes.
you are doing and Manasvi may be doing.
Yes.
Adit, are you doing?
No,
you.
sir. I'm catching up on the older topics from 11th grade. So like the earlier ones we did, like NLM and stuff.
Yeah, great. So no problem. So anyway, but still I'll keep at least one complete doubt lecture on next week. It will be on most probably Wednesday or something. So you have to find some extra time.
Yes.
Okay. So okay, bye guys. Take care. See you next class.
Good night, sir.
Good night, so guys.